Okay, welcome back to Unit 5, Day 7, Part 2b. This is example 3. So this example, like the other examples, is asking us to write the balanced equation for the combustion of this organic molecule. The only difference in this molecule, or this example compared to the previous ones, is that this molecule has oxygen in it. The other examples just had carbons and hydrogens. So that means it'll be a little bit tricky, but we'll get through it. So the first step is to write the unbalanced equation. I'm going to take my organic molecule, C3H7OH, which is the same chemical formula for isopropyl alcohol, so we'll assume this is isopropyl alcohol, plus my other reactant, which will be O2, and my two products, CO2 and H2O. Now, in terms of order, you can put H2O first and CO2 second, that doesn't matter. The next step is to list the number of atoms I have on both sides, so carbon, hydrogen, oxygen. On the reactant side, I have 3 carbons. Here I need to be tricky in this chemical formula because the hydrogens are sort of split. So I have 7 plus 1, so I have 8. And I also need to be careful because we have oxygens in more than one molecule here. So we have 1 plus 2, 3, so a total of 3. On the product side, we have 1 carbon, 2 hydrogens, and 1, 2, 3 oxygens. Okay, so now I want to go ahead and start balancing the equation by changing the coefficients, remembering to balance my oxygens last. So starting with carbon, I have 3 on the reactant side. If I want 3 on the product side, I use a coefficient of 3 in front of CO2. And then I remember to change the number of oxygens now because I have 3 times 2, which is 6, plus the 1 gives me 7. Now I can go ahead and change the number of hydrogens to try and get those to balance. I have 8 here, and I have 2 on that side. So to get there to be 8 on the product side, I add a coefficient. I multiply H2O by a coefficient of 4. So that gives me 8 hydrogens now. I got to go ahead and change the oxygens as well. So this was 6 plus now 4 gives me a total of 10. Okay, so far so good. And now we're up to the part that can get a little tricky when you're dealing with a molecule that has, organic molecule has oxygen in it. But like I said, we'll get through it. So the process is still, or the thinking is still the same. We want to figure out what coefficient that we can change in order to get there to be the same number of oxygens on both sides. And I have 10 on the product side, so I want to try and aim for 10 on the reactant side. Now the only thing here though is that on the reactant side, one of my 3 oxygen comes from C3H7OH. And the other one comes from O2. Now typically what I want to aim to do is just change the coefficient in front of O2. But like I said, I already have 1 from the C3H7OH. And if I want to get to 10 on this side, that means I only need 9 to come from the O2. All right, so to figure out the coefficient in front of O2, I basically take the number of oxygens I have in the other molecule, or the number of oxygens I'm aiming for, so 10, which is what I'm aiming for, minus 1, means I need 9. I want to have 9 from O2, okay? All right, so now I'm asking myself, what times, 2 times what will give me that 9, right? Because if I have 2 times that number, I get 9 over here plus 1 over here, I would get 10, right? So the number that I can multiply 2 by to give me 9 is 4.5. Now remember, that is not a whole number, but that's okay because we can always go ahead and change it. So I do now have a total of 10. If I were to tally it up, I do have 10 on this side. 4.5 times 2 is 9, plus the 1, I've got my 10. All I need to do now is just convert that from a decimal into a whole number by multiplying all of the coefficients by 2, right? Because I need to multiply this by 2 to get it to be a whole number. So I need to do that to all of them, just like what we do in math. Whatever you do to one side, do to the other side. So this will give me a coefficient of 2 in front of the C3H7OH. I get a coefficient of 9 in front of O2. I get a coefficient of 6 in front of CO2 and a coefficient of 8 in front of H2O. Okay, so now I can go ahead and rewrite this. 2 times C3H7OH plus 9 times O2 goes to form 6 CO2 and 8 H2O. Now, one good strategy that's super helpful, and I haven't done the other videos, but I probably should have done, is just to go ahead and check it and make sure everything works out. So we're going to make sure the number of atoms are the same on both sides. So right now we have, for carbon, we have 2 times 3, so we have 6 on that side. For hydrogens, we have 2 times, well, this is 7 plus 1, so that's 8, times the 2 will give me 16 hydrogens. And for oxygens, we have 2 from this molecule, so 2 plus the 9 times 2, which is 18. So 18 plus the 2 will give me 20 oxygens. All right, let's see what we got on the other side. So for carbons, we've got 6. Hydrogens, we have 8 times 2, which is 16. So far that's looking good. And for oxygens, we have 6 times 2, which is 12 from the CO2, plus the 8 from the water. 12 plus 8 will give me 20. So this molecule, this equation is balanced. All right, that's it for example 3. Now you have your CFU that you can do, which is writing the balanced equation for the combustion of C4H10. The next video will show you the answer for that, but you want to try that on your own.